Outlines on objects are one of the objectively coolest things you can add to your games, but as the width of the lines gets larger, most brute force methods of drawing them really struggle with performance. Today, I've collated the research and techniques of several avid programmers, along with my own discoveries, to present to you a beginner's guide to jump flooding, a fast way to get thick outlines. Now, Godot 4.4 came out this week, and it's fantastic, and I wasn't a contributor on this one, so there's no conflict of interest. But despite my previous comments on the subject, we don't believe in engine supremacy on this channel. In fact, we don't believe in any kind of supremacy. Everything sucks and that's fine. Great, even if you're an engine programmer. The work never ends. But I'll be using Godot to showcase how this works because its compositor effect system uses really low level tech, and teaching you how it works at the simplest possible level will allow you to apply the same principles wherever you want. Okay, so how do brute force algorithms work and why are they so bad? Most design programs such as Photopea, where the outline or stroke is an effect that only needs to be applied in one context, will probably use an algorithm like this. Here's an image we'd like to outline, totally chosen at random. For the sake of simplicity, let's say we're just trying to outline the outside of the image. For a 1 pixel outline, we pick any pixel on the outside of the image, then test its neighboring pixels. If any of these neighboring pixels are inside the image, then this pixel is part of the outline, otherwise it's not. If we do this for every single pixel, we'll have a 1 pixel outline. We can also make it a little more efficient by doing 2 separate passes in both the X and Y direction. You'd think 2 passes would be twice as expensive, but the real performance cost is the reading of the texture when we check a pixel, which separating the passes reduces by about 30%. For a 2 pixel outline, however, we're already seeing the problem. We need to check 2 pixels in every direction, including diagonally, which means almost twice as many checks. This increases exponentially as we increase the outline width, meaning we could be checking potentially hundreds if not thousands of pixels per pixel for higher widths of outline. It's also worth noting that these checks need to be done in a circular pattern for smooth lines, which means we can't separate the axis anymore for performance gains. This kind of performance hit is fine for a one-time calculation of an image editing program, but it doesn't work so well in real-time game environments. So what can we do to improve it? Well, to start, we might get away with only checking the outside of the circle. Thanks to basic circle equations, this means wide outlines would decrease performance linearly instead of exponentially. But this would definitely involve some more complicated maths, as well as producing artifacts if part of our image is smaller than the given radius. There are some other methods, like blurring or doing some crazy stuff with bitmaps. If you're interested in these techniques, then you can read Ben Golis's article on the subject, The Quest for Very Wide Outlines, on which the principles of this video are based on. In the end, Golis's research turns up that the jump flooding algorithm blows all of them out of the water. So what is the jump flooding algorithm? Well, the problem we're trying to solve is essentially a distance problem. We want to get the distance of each pixel to the nearest point of the image. Then, when a pixel is below a certain distance, we color it as the outline. JFA, introduced by Rongyeo Dong, was built to generate large-scale distance fields in an efficient manner. Let's say we want an outline of width 7. Let's start by taking our image and coloring it in, with each pixel of the image representing its position on the screen. Now let's pick a pixel and look at these 9 positions around it, distance 4 pixels away from the center. For each of these positions, we check to see if there's a position stored there, and if there is, we calculate its distance from our center pixel's position. What the closest pixel ends up being will be put in the center pixel slot. For pixels inside the image, nothing changes. The center pixel stores its own position, so its distance is 0 and it's always the closest. But now look at what happens on the outside of the image. They're storing the closest positions of the image that are 4 pixels away. It's a little easier to understand if we show arrows from each pixel to the closest pixel they found so far. As you can see, we're clearly not done yet. So we do another pass, this time with an offset of 2 pixels. Remember that we run the algorithm on already filled in pixels too, using previous calculations to attempt to find a closer point. This looks better, but it's still not correct, so we do one final pass with an offset of 1. Now, with a small degree of error, every pixel in this outline is storing the positions of its closest point on the image. And if we take the distance between each pixel's position and its closest point, we get a distance field. And if we color in every pixel that has a distance of less than 7, we get our outline. Each pass has the same number of image reads, and there's only 3 passes, so this is significantly more efficient than the brute force approach from earlier. But what if you want an outline with a width of 6 pixels? Well, you run the exact same algorithm, and then just color in the pixels with a distance of less than 6. But what about 10 pixels? For that, you need to do an extra pass at the start, this time with an offset of 8 pixels. This will give you the same distance field as before, but with a width of 8 extra pixels and only 1 extra pass. For any width, you need passes starting the lowest power of 2 that is larger than your width, which looks like this function. That means for twice the width, you only need 1 extra pass. For 8 times the width, you only need 3 extra passes. At crazy huge widths, this algorithm completely destroys all other approaches, as shown in this handy graph Golis made. And the only time it's worse is for outlines that are 1 pixel thick. And the best part? You may have noticed that every check we've done has been in a square, like earlier with the 1 pixel outline. That means we can split each pass into 2 X and Y passes again, reducing the total number of texture reads. Technically, there's an argument to be made that this doesn't save that much on performance and introduces a higher margin of error, but in practice, it looks like this hasn't been observed. So how do we go about implementing this algorithm? Well, Godot's compositor is quite complex and requires a lot of boilerplate. I know a lot of developers are working to make this a bit more user-friendly, like Garrett Gunnell, aka Acerola, and I honestly can't wait for that. Having to manually recompile shaders and hunt down bugs in RenderDoc is a huge pain, and this shader ended up requiring way more trial and error than I initially signed up for. I did use a base class from Pink Arcana's JFA implementation to cut down on a lot of the boilerplate for writing compositor effects, but everything else in the video is my own implementation. Pink Arcana's work is great, by the way, link in the description to check it out. I've set up my main scene so that there's a main camera rendering the screen and a second camera with the exact same setup that only renders objects on these specific layers. I want this outline effect to be object specific, so we're going to use the output of this second camera for our JFA pass. The second camera is under a sub viewport, but unlike previous videos of mine, we won't be using its output texture at all, thanks to a nifty little trick. So we're going to build 2 compositor effects, a JFA pass that applies to the second camera, which will create our JFA distance field, and an overlay pass that takes the output of the previous pass and overlays our outline onto the main camera. Using the base compositor effect class as a parent, our JFA pass looks like this to start off with. We'll need 2 shaders for this, a mask shader to take the input of our camera and figure out what we want to apply the outline to, and a JFA shader to perform 1 pass of the jump flood algorithm with a specific size and direction. All shaders start with this base code. There's a lot of boilerplate, but there's nothing you have to worry about. Just know that the code here will be run for every single pixel in our image. Also, if you've worked with shaders before, you might note that I'm not using any samplers. This is because all of the images, or buffers, we're working with are exactly the same size. So we don't need to interpolate between any pixels, and reading the image directly is technically slightly faster than sampling it on most hardware. Because of fun technical quirks, however, the depth buffer can't be read like that, so we will be using a sampler here, and everything I just said is going to feel redundant. We sample the depth buffer, and if there's something on the screen, that means we outline it. This is where it writes its position onto the pixel. The JFA shader is a bit more complex. We add these constants to tell us the offset we're working with, and whether or not we're checking in the X direction. Then, inside the shader, we check the 3 pixels in the specified direction and compare their distances to find the closest point. I'm using square distance here because the square root function is the work of the devil, and we don't actually need it here. Also, the dot product of a vector with itself is the same as the squared magnitude of that vector, in case you didn't know. Back to our compositor effect, we want to compile these 2 shaders and create their pipelines. Most shaders, like the mask shader, only need 1 pipeline, but for the JFA shader, we need 1 for each offset in each direction. We'll also need 2 render textures, the same width and height of our screen, so each JFA pass can have an image to read from and an image to read to, plus some default uniforms that tell our shader how wide the screen is. Then, on our render thread, we'll have some boilerplate again to make sure everything is set up correctly. We'll write a mask pass function that will take the sampler uniform from our depth buffer and pass that into the mask shader, outputting into the first of our render textures. Then we create a JFA pass function that uses specific power of 2 and a direction. And we run it the required number of times. Finally, we pass a reference to our result into a static variable to use in our other compositor effect. There's probably a smarter way to pass this information. I tried using viewport textures, but that gave me so many headaches when it came to precision. Finally, we just need to set up the overlay pass. This is thankfully really simple, using a single compute shader, taking the reference we set up in the previous phase and adding a bunch of extra data for the outline. This overlay shader is also pretty simple. It takes the data given, computes a distance field, and then uses that distance to create the outline. Again, we're using the square distance here for a small performance benefit. It'd be handy to be able to write to the depth buffer in this pass so our outline would correctly interact with transparents, but sadly that's not supported as of Godot 4.4. Then we just add our compositor effects to the relevant cameras, add an extra script so the second camera will always follow the main camera or the editor camera if we're in edit mode, and presto chango, we've got some thick outlines. You can also use these distance fields for all sorts of fun effects, like a sliding ripple or even an angry noisy outline like in that one Mario game with the feet and the balls. And all of it for a significantly smaller performance cost than its brute force ancestors. And just a reminder, but if you feel I went too fast, YouTube has a handy slowdown function, and I put all of my steps inside the description, because let's be honest, text is the far superior method for learning this stuff. Also, I personally write the subtitles for all these videos because I hate YouTube's auto-generated captions. I hope you've enjoyed the video so far. Let's hear a quick word from our sponsors. That sure was quick. Do you want to hear it again? Sorry it's been so long. As per usual, life and my career got in the way. Rubel's doing well, though he's grown to such a size that we think he's part panther. The big news is that I got engaged, but I also got a new job last year that is very top secret and I'm not allowed to talk about. So if anyone asks, I'm unemployed. I think that's how NDAs work. Oh, and I'm on a podcast now, Don't Stop Recording, where me and lifelong friend, journalist, and fellow game developer Jacob Hayes do fun little reviews about found footage media. Season 1 plus the Halloween specials are all available to stream now wherever you get your podcasts. We've got some really fun surprises in store for Season 2, so look out for that trailer soon. In regards to the channel, I'm going to try and stick to a schedule that balances both my interest as a tutorialist and my want to experiment with other video formats. So hopefully this gives you some incentive to subscribe. The schedule will be a holy trinity, starting with a graphics video, that's this one, and then a generalist game dev video that will hopefully be the start of a new series. And then a Matt Redman special that is whatever I feel like doing, and we'll go round and round and round until I die or you stop watching. Like and subscribe, and thanks for stopping by.